Okay, in this video we're going to take a look at some infinite sequences. And there's a number of different ways that infinite sequences can appear. One of them is if they can be rewritten or written as a single expression. So if we take the sequence 1, 1 over 2, 1 over 4, 1 over 8, and we keep going with that pattern, that can be seen as a function f of n is equal to 1 over 2 to the n, where then n is 0, and then n is 1, and then n is 2, etc. Or if we took the sequence 0, 1/2, 2/3, 3/4, 4/5, this could be thought of as f of n is equal to 1 minus 1 over n, and then we just need n values that are bigger than 1. Or you could just have a sequence that alternates, like -1, 0, -1, 2, 3, -3, 4, and that continues. And this could be an expression where you have a -1 to the n that controls the switching from positive to negative, and then just the n value. And again, this is for n greater than or equal to 1. So these are some types of sequences, infinite sequences, that can be expressed with just one single expression. Of course, other sequences or other types of sequences might be defined recursively. We've seen this before with Newton's method, where the next term is equal to the previous term minus the function evaluated and the derivative evaluated at the previous term. And another example of this is where you start off with, say, a1 equals 1, and then you define other terms to be, say, 1/2, take the previous term, plus 2 over a n minus 1. So some sort of recursive sequence like this. And what that ends up looking like is, well, the first term is 1, and the second term is 1/2 times 1 plus 2 over 1, and you end up getting 3 over 2. And if you keep going with this, and I'll just quickly give you a3 and a4, you start to get a list of 1, and then 3 over 2. I'll show this as decimal places, so that's 1.5, and then the next one, 17 over 12, is 1.4167, 1.414216, and you keep going. And I'm not sure if you can see this or not, but this list is getting closer and closer to a particular value, and that value is the square root of 2. And this idea of an infinite sequence getting closer and closer and closer to a particular value is called convergence. So let's take a look and see how convergence is tied into limits. So let's take a look at an example. If we have each term being equal to n plus 4 over n plus 1, let's see if we can prove that this converges to 1. And the way that we can do that, so let's just list out the sequence. The first term is 5 over 2, the second term is 6 over 3, the next term, if I add another one in, is 7 over 4. And this pattern continues. We want to show that this gets closer and closer and closer to 1. Of course, way up here is like 1,000,004 over 1,000,001, so it does seem that the decimal places will get closer and closer and closer to 1. So since this a sub n can be written as the function, basically f of x is equal to x plus 4 over x plus 1, we can go and use limits, as we have previously in this course, to explore what's actually happening. And of course, the limit as x goes to infinity of f of x, this tends to converge, or this tends to go to 1, and therefore this shows the convergence of a of n as a list converging to 1 as well. Similarly, if we have a list that's given to us, so 2 squared over 2 squared minus 2 over 2 squared, and then 3 squared minus 2 over 3 squared, and 4 squared minus 2 over 4 squared, etc. We can think about this as the nth term will be n squared minus 2 over, and this can simplify to 1 minus 2 over n squared. So you can make this your function, 1 minus 2 over x. You can apply the limit as x goes to infinity to this function, and this becomes 1 as well. So this sequence, will converge to 1 as well. And there are limit laws for this type of convergence. So if we start with one sequence a sub n and another sequence b sub n that are convergent sequences, that way we know that as we go closer and closer to infinity of a sub n, we get L because it converges, and b sub n we get M as it converges. Then we can apply these limit laws. The first one basically being an addition limit law, where if you have the two sequences added or subtracted, then if you apply the limits to each part, you'll get L plus or minus M. If we have the limit of the multiplication of the sequences A and B, we get L times N. If we have the division of those two, of course, we get L over M, and there's some conditions on that. Of course, M can't be equal to 0. And if we multiply by a constant, so we have the limit as n goes to infinity of some constant value times one of the sequences, you just get that constant value times the convergence number. We also have a squeeze theorem for these sequences. So if we have three sequences, a sub n, b sub n, c sub n, and some m value, and if a sub n lies in between c sub n for values of n that are greater than m, and if we have the convergence of the two outside limits, so b sub n and the limit as n goes to infinity of c sub n, and they go to L, that automatically forces the a sub n to go to L when you apply the limit as n goes to infinity to it. So this is the squeeze theorem for sequences. Okay, let's see if we can put this together with an example. So let's see if we can show that for f sub n, or f of n is equal to n over e to the n, that this thing converges, and see if we can find its limit as well. So we change this into the function, or think about it as the function, x over e to the x, and then we can try and apply the limit as n goes to infinity of x over e to the x. And unfortunately, this turns into infinity over infinity. But we have some tools that can help us, and one of those tools is L'Hopital's rule. So if we use L'Hopital's, we can take the derivative of the numerator and the derivative of the denominator, which is 1 over e to the x, and now when we apply it, we get 0. So this function or sequence, a sub n, this converges, and it converges to the value of 0. Let's try one more. If we have a sub n, and this is an alternating sequence where they flip from positives to negatives, 1 over n. So if we try some of these same techniques and think about this as f of x is equal to negative 1 to the x times 1 over x. So if we try to put the limit as x goes to infinity to this, we run into a problem because we have negative x and then positive x and then negative x and positive x. So we're going to try another technique, which is to use the squeeze theorem. And if we notice that negative 1 over x is always smaller than negative 1 to the power of x times 1 over x, and that's always smaller than 1 over x, then we can use the limits as x goes to infinity of each of these end pieces. So limit as x goes to infinity of 1 over x to generate what is the limit as x goes to infinity of negative 1 to the x 1 over x. And of course, these end pieces are equal to 0, each of them. So instead, we can use the squeeze theorem to solve this one and show that it squeezes into 0, which therefore shows that a sub n converges, and it converges to 0 as well.